2 million Americans that went across the ocean, and they didn't have a whole fleet of ships in 1917 to do it, and they called it the Emergency Fleet Corporation, and they got, and it turns out the Germans scuttled, when the war was declared, the Germans scuttled every German ship in every port in the United States. I mean, they tried to destroy them, and I can give you articles from a history of welding of how welding was used to repair and bring these ships back into service, okay? Even though the Germans tried to pull them up in the harbor, okay, as they sat there. So welding was important, and Comfort Adams realized that welding should be important in any form of the American Welding Society in 1921, okay? But that's about the time that arc welding started to pass resistance and oxyacetylene. In Europe, we actually know who it was. In Göteborg, Sweden, one welder stuck his bare steel electrode in the mud and welded with a muddy electrode, and that's the basis of shielded metal arcs, mineral-coated electrodes. Now we have special mud that costs about $10 a pound, okay? Very chemically controlled. We use things like old tobacco stalks for the cellulose. Anybody know why we use old tobacco stalks? That's actually a proprietary secret of working electric. It's not much of a secret. Tobacco concentrates rubidium from the soil, and rubidium helps with arc starting. And in covered electrodes, they use the cheapest materials you can imagine. And what could be cheaper than old tobacco stalks? I mean, it's good for nothing other than fertilizing the next season's tobacco, right?
So is that the concern as the tobacco industry declines, that they're going to have issues with the welding industry?
No, they could always get their rubidium from other sources, okay? But rubidium by itself is expensive to buy it in concentrated form, but you gotta have cellulose, so tobacco stalks give you both, right? And that's certain little tricks that people in the industry have learned over the years, how to get the cheapest product to make, actually, which are very high quality electrodes and stuff. But we don't even use stick electrode anymore, or as much. Back when I was your age, we were 70% stick and 30% gas metal arc. Now it's the other way around, if it's not 80-20, okay? And it's been transitioning like that for my career, okay? And there's good reasons for it. Mainly, you get 60% arc time with gas metal arc, and you get 25% arc time with stick. It's just straight economics, okay? So anyway, those are some things that you kind of need to learn, because none of you are going to have to go out there and weld up a ship, okay? You hire people to do that, but you are going to have to know what they're doing and whether they're giving you a load of bull, okay? So that's part of hopefully what you'll learn about some of these things. My first student ever, who actually worked on welding of titanium for an Office of Naval Research contract, went to work for Electric Boat, and he retired from Electric Boat a number of years ago as one of their welding engineers. When he started out there in the 70s, he was one of like 37 welding engineers. I think when he retired, he was one of 6. I mean, the kind of production had tailed back, and they had streamlined things, and they were going to gas metal arc rather than all stick, and nearly all stick and stuff. Still need some stick, because you can't even get a gun in there in some of the places these guys have to weld. And you look at where these guys have to weld, and you say, boy, I'm glad I don't have to do that job. Okay. But those guys, hey, they're cowboys or bikers or whatever. Any of you been in an electric boat? Served an electric boat? Yeah, so you know what the parking lot looks like at lunch?
Yeah, it's ridiculous.
It's ridiculous. And you think, these guys are building nuclear submarines? It looks like a Hell's Angel convention, right? Out there in the parking lot. And they're all out there doing their things, which are probably not, well, it's probably classified because no one wants to know what they're doing in their lunch hour, right? But anyway. Okay, so today I was going to talk about titanium. What else do people, any topics you want to talk about? Because I mean, I can come up with stories in most cases for things, and that's what students usually like, is to hear the story. stories. And some of them are firsthand. You'll hear some of them today on titanium. Has anyone decided whether they're ready to give a talk this week?
I'll go Thursday.
You go Thursday?
Yeah, I can go. I can Thursday, Friday.
Okay. Any others? Any other takers? Okay, well, I got two of you. Why don't we have both of you go Thursday? It's 10 minutes each, and I'll fill up the rest of the time, and we'll talk about whatever. What are your topics?
So I was on Freedom of Fort Worth, LCS 1 and 3, doing a lot of corrosion issues. So
Stress corrosion cracking.
it was more of improper choice metals. So
Oh, okay. Dissimilar metal corrosion?
yes.
Okay, yep, okay, yep.
Aluminum welding on the same ship
Oh, okay,
from my last job.
okay. Fine, so every time the Navy goes to a new material, they have problems. And we could talk, and that could be part of the rest of the talk. How when they went from the typical ship steels, which are like 50 KSI, which was, after World War II, a ship was a 50 KSI steel, this kind of a carbon steel. They call them ES grades in the commercial Navy, not commercial Navy, commercial shipbuilding. But they decided to go to the HY steels, the high yield steels. And they started welding HY80 in when they first started doing it, they had hydrogen cracking problems. And supposedly a couple of the first vessels, they just gave up because they wanted to complete them, and they used stainless steel as the filler metal, which meant that they had 80 KSI plate with 40 KSI filler metal. Okay, so that sort of limits your depth. Okay, but we can talk about when they went to HY100. And turns out John Galati, my first student, was in charge of the first couple of hulls that they put whole sections of HY100 in. And they were HY80 designs, but they just wanted to get some experience with building a whole section, a modular section of HY100. And then the Seawolf came along and they decided to make that all out of HY100. And there's the story how some people wanted to make it out of HY130 and how some people felt they couldn't do that. Couldn't, okay? But other people felt, well, we spent $50 million in the 1960s developing HY130, we want to use it. Except they never had to weld it, okay? And I actually was the whipping boy that NAVC sent in to talk to the chief engineer of the Navy and tell him he couldn't do it, okay? So I can tell you some of those stories. You won't find some of those stories in the textbooks or other places, but anyway, so we can talk about some of those things. That means I think that I will probably spend the other time this week, and we'll have class every day this week, just talking around some corrosion stuff. And I think we'll probably do next Monday, but I'd like to get some more people to start talking about doing things next week, okay? So start, Cody, line them up.
Go.
Get out your whip. Give them a piece of paper and tell them to sign up, okay? Believe me, you're going to have more time to put this together now. And when almost all of you raised your hands when I said, did you have to give a talk when you left? And you did. And even if you don't want to give that talk, you can just go look up USS Thresher on Wikipedia and give that talk, okay? I've heard that talk half a dozen times, okay? Okay, yeah.
I had emailed with you yesterday, but I plan on doing a space vehicles or launch vehicle application, which is...
Yeah, you sent me an email or something about that, right? Yeah.
Do you have, I searched the lectures online, do you have any specific lecture material on that? You seem to have a lot of stories about it, understanding like the space plane seems like you're on.
Well, yeah, I had to look at the X-33 space plane and why that thing failed. I sent around a piece of the X-33 yesterday. I don't have as many Air Force stories, okay? Because you'll see a little bit today. A lot of my career started out working with the Navy stuff. In fact, one of the reasons I teach this course, because I don't get paid during the summer, is because the Navy, I probably would not have gotten tenure at MIT if the Navy Office of Naval Research hadn't taken me under their wing and given me a bunch of money, okay? And I still feel a certain sense of responsibility, duty, payback to the Navy, okay, even though I don't have as close a ties as I used to. My father went to the Naval Academy. How many of you were Academy grads? Okay. But you know, my dad got through in 3 years, okay? Class of 44 graduated in 43. They got to go 12 months a year, no days off, okay? Didn't even get to go home, okay? Anyway, so let's talk about, so think about what you want to talk about. If you want, we can talk after class. I think that's what I said in the email.
Sure.
About what you might want to do, as far as that goes. I did bring these things, which we can pass around, that I often point out. One of the reasons for doing the corrosion thing is not because it's required by NAVC, but because the Navy is the corrosion leader, okay, among the 3 services. You know, they break up responsibilities now because of the military downsizing in the last 25 years. And like, the Army is responsible for ballistics and armor, okay? And the Navy is responsible for corrosion, okay, for the 3 services. And there's a reason. You guys are surrounded by salt water. What's more corrosive than that? So this actually is a turbine blade, or three stators that go in a civilian engine. This came off of Mexican Airlines commercial jet. And if you look carefully, you'll see down here a little just different color, a darker color down at the bottom. That's because these have already been repaired once, and they put a aluminized layer on there to help with the oxidation resistance. This is one that came out of an operating engine, and it had a lot of other blades like that, that had failed due to sulfidation corrosion. Okay, and we might talk about that sometime, but just to give you an idea of some things. I mean, this looks like a postcard cutter. This one that's
That failed in operation.
It didn't fail.
What's this? What's
That's
this honeycombing?
the honeycombing is the seal. Okay, when the thing's spinning, you actually put a honeycomb in there, and as the blades get longer in service, they rub up against. They're intended to rub and seal the surface, and so the amount of elongation of the blade in service is approximately the thickness of that honeycomb layer. But it forms a very good seal because it's a wear seal.
So it's just due to heat and angular momentum? Like it spins, like these grow in length over time?
Yeah, the heat, the creep of the metal. The metal under stress, radial stress, centrifugal stress, grows over time, but you have, the whole efficiency of the engine has to do with how good the seal is. And the original engines, which were not very efficient, maybe we'll talk about that a little bit here, they basically just had labyrinth seals, which were kind of rings that passed each other, okay? But eventually they got into the honeycombs, which actually you're using a wear surface. So that's a very good seal, okay? And they can, I think they're at, there's less than 1% loss, you know, because you lose anything, you're losing compression, which is the whole compression, pressure and temperature, that's what makes the engine runs, right? Okay, so let's talk about titanium submersibles. And there's both civilian and military reasons for using titanium in submersibles. But some of the positive reasons to want to use titanium, it's high strength, lightweight. And why do you need high strength and lightweight for a submersible? To come back up. You'd like to, if you lose power, you'd like to just let go of some ballast and float to the top. And that works best for high strength and lightweight. Okay, you can go deeper with high strength and lightweight. Okay, you want something, you'd like to have something that's corrosion resistant. The Achilles heel is steel. You're not taking my material selection things where I talk about steel is 90, where I talk about 97% of all metals. But the Achilles heel is its corrosion resistance is states. Unless you're from the steel company, you know that everybody has to replace it every 30 years. Okay, so, but titanium essentially lasts forever. We use it as medical implants in the human body because it can tolerate that saline solution for the life of the patient. without any noticeable corrosion. And it can do that for ships too. And in fact, you know that when they went from a 30-year lifetime on a ship to now what they're kind of advertising ships are supposed to last 50 years, okay? They had to get away from carbon steel because most of the carbon steel was full of holes after 25 years, okay? Any of you who serve on those ships?
We still do carbon steel inspections all the time.
Well, you do them for the first 2 years, okay? But in any case, but with titanium, a bit more expensive, lightweight, thin wall, and should not have any real corrosion problems. Anybody know of any corrosion problems in titanium piping?
It's not really corrosion, it's just titanium piping, there's a lot of corrosion inside of it. So
Yeah. Yeah, you can have biological growth and other things. So now we do that in land. We actually put biocides in the water in our boilers and things. Well, you do that in your boilers too. Well, actually, you probably don't.
Oh, we just use chlorine generators.
Yeah. Okay. So anyway, there's different ways to do things. And another big military thing is non-magnetic. And why do you want to be non-magnetic?
Signatures.
Signatures. And signatures what?
Mines.
It turns out the superconducting quantum interference device is SQUID. Anyone ever heard of a SQUID? I'm not talking about the ones you eat, you know, but this is a device that was invented by Brian Josephson in 1962. He was about 22 years old. He didn't invent the SQUID, but he discovered the Josephson effect. He was a 22-year-old graduate student at Oxford or somewhere, and his professor didn't have time to talk to him, so he gave this new student a standard problem to go solve this math problem. And Brian was so stupid, he didn't know you were supposed to throw out this inconsequential term that made the solution of the differential equation. See, you guys are learning how to solve these problems, right? Maybe one of you will make a mistake on your homework problem and win the Nobel Prize. But Brian essentially didn't know to throw out this term. He solved this incredibly difficult problem with this extra term, with this complete term in it, and discovered the Josephson effect, which actually says that even for DC currents, you actually get an AC component with your superconducting energy flows, and it's now known as the Josephson effect. And with the Josephson effect, you could measure very, very precise magnetic fields. So I met Brian Josephson in about 1970 or so. He was here. He had already won the Nobel Prize when he was like 24, 25, and he was an absolute basket case, okay? He was not ready to win the Nobel Prize in his mid-20s, and everybody thought he was the brightest guy in the world. He knew he had made a mistake, okay? But he was smart enough to recognize it was something unusual. In any case, at that time, in the 70s, a plane flying overhead with a superconducting squid could detect something under the water that was long and magnetic, okay, for the magnetic signature. It was projected, I remember, in the 70s that sometime in the 80s, a satellite from 100 miles up could do the same thing with the improvements in squids. So, and I haven't kept up with it, but I suspect that right now you don't have to fly a plane over. When you fly a plane over, you probably boom, and there's a signature, okay? But even the satellites can pick these things up. So the Navy spent a lot of money in the mid-90s. They were looking at austenitic stainless steels. In the 60s and 70s, they were looking at titanium. They looked at composite materials like the X-33 space plane material and whatnot. Some of the cautionary things are fabrication. It's much more difficult to fabricate titanium. We'll talk about that. Titanium doesn't have the toughness. You know, I broke this piece of plastic yesterday. Titanium's more brittle than steel. Okay, steel has 2 to 3 times the toughness of titanium for equivalent strength levels. So it's best not to take a depth charge in a titanium submarine compared to a steel submarine. As Professor Flew used to say, the Navy HY steels allows the people in the submarine to be slowly crushed to death, whereas, you know, in the other submarines, they just break apart. You'll drown. Anyway, fabrication, toughness, and repairability. One of the advantages of steel is it's easy to repair relative to almost all other materials, including aluminum. And the real problems are cost and creep fatigue, okay? So what about the cost? Well, one of the problems in the cost is HY steels cost about $2,000 a ton, give or take, okay? Titanium is about $100 a pound, or $200,000 a ton. Right, anyway. That's a little 50 times the price. So if you think of a submarine like the Seawolf, which was supposed to be at the time a $2 billion submarine, the hull mechanical and electrical, basically the hull primarily, was a $500 million. Okay? The rest of it was all those missiles and electronics and sonar, and they add up. That's the big ticket items. And this is all sort of true in surface ships too. It's the armaments and stuff. It's not the hull that's so fabulously expensive. But in any case, if you start saying, well, if the hull of the Seawolf costs you $500 million, then a titanium sub might cost you $25 billion. And you start saying, I don't know if we can afford very many of those. Okay, more expensive than a carrier. Okay, the buy-to-fly ratio in shipbuilding in general is less than 50%. The buy-to-fly ratio is an Air Force term. It's how many pounds of metal do you buy to how much actually goes in the aircraft, and that's why it's the buy-to-fly ratio. A lot of aircraft components used to be in the 2% range. You buy 50 pounds to fly 1 pound, and so if you're buying something that costs $30 a pound, a nickel-based superalloy, all of a sudden the price goes up by a factor of 30 to $1,500 a pound, okay, for the part that's been cast and forged and machined. You machine away everything for lightweight, but then your costs, your material costs, go astronomical on some of these things. Shipbuilding's not so bad. You start out with these rectangular plates, and you cut out these funny shapes, and you bend them and stuff, but you still are going to get less than 50%. Half of the material you buy from the steel mill goes back to the steel mill to be remilled. Okay, so your $2,000 a ton becomes $4,000 a ton. And I remember there's the materials research needs for the 21st century. I actually referenced, there's an article in there, a study that NAVSEA had Newport News do around in the mid-1990s. They were looking at the weight of the Nimitz class submarine. And the Nimitz class submarines were gaining an average of 250 tons a year. I mean, I gain a little weight every year, and so do the subs. Not subs, but aircraft carriers. We're gaining 250 tons a year. If you just plotted from the 1960s into the 1990s, and you saw they were starting out in the 60,000 ton class and going up to the 75,000. So that's when the Navy started saying, we need to spend $50 million to design a new hull. What's your new hull called?
Ford.
What?
Ford class.
Ford class, okay.
It's the same hole, same hole.
Is it the same hull?
Yeah.
So that's what I had heard, that they decided they couldn't afford to design a new hull. But I thought they had the bulbous nose on now.
The Nimitz does do that.
Yeah.
The newer Nimitz class has the bulbs on.
Okay, well, anyway, I mean, I'm not a ship designer, so that's what you guys are here to learn about. But in any case, so they were trying to figure out, well, could we go, a lot of the steel on a carrier is just regular old ES grade 50 KSI steel. And they wanted to know, well, if we went to HY 60, okay, or HSLA 60, could we save money both in welding and material costs and weight and stuff? And they found they could take out 2,000 tons out of a carrier if they went to HY 60, but it actually showed that the as fabricated cost was $10 a pound, okay? Now I actually happened, and the cost of buying the raw material was $1 a pound. And I actually had a rule of thumb that I was teaching in my course, that the material costs are only about 10% of the as fabricated cost. The as fabricated cost will be 10 times. This is after inspection and design and scrap and all the, you throw all these other things, and you can take my material selection course, which you're not, but I had this little, actually it's in, that table is in the 21st Century Defense Needs article, okay? So I was teaching this and I found out NAVSEA spent over $1 million on this study at Newport News, and they found that the as fabricated cost of the HY60 was going to be 10 times, or $10 a pound, which was exactly what I've been teaching. And I would have done that study for a lot less. Okay. But in any case. So you got to remember that the raw material cost is just a small fraction of the whole thing. Fabrication requires a clean room environment. I'm going to go through that in a second, but I used to tell people down in Washington, you can't build a titanium ship in the same shipyard that you build a steel ship. Okay? It's going to be more like an aerospace facility. Okay? It looks a lot. It's going to look a lot different. Basically, when welding titanium, it's kind of white gloves. If you clean titanium before welding, you better not touch it with your fingers, because that fingerprint will introduce porosity in the weld. Okay, and I've got a story on that a little bit. Okay, infrastructure does not exist in the country. The titanium, Nimitz, the world's largest outside of the Soviet Union titanium company, basically leases time each month, about 1 or 2 days a month, at a steel mill to roll their titanium ingots into plate. They could not afford a $1 billion mill to roll titanium plate because they would only be busy 3 or 4% of the time. Okay, so the titanium industry is not big enough to really support, you know, a fleet of ships. Okay, of heavy walled ships. No industrial experience with heavy section joining. After the Alpha Slug class came out, or was announced in 1979, I remember my first trip to Europe. I was coming back, and I was on the airplane. I was reading the International Herald Tribune, and there was an article on the front page of the new Soviets now had a titanium submarine. It was 1979. They had actually laid the keels for the first Papa class in 1964. Okay, and I'm sure the U.S. Navy knew about this because my first research contract was in 1977 with the Office of Naval Research. It was for welding of heavy section titanium, and here are some of the welds that I kept. Pass them around and show you submerged arc welding of titanium. These were welds made by John Galati in 1978 or so. Okay.
I'm sorry, as the non-Navy guy in the room, when you say submerged arc welding of titanium, that's titanium to titanium.
Yep.
Doing it.
Well, we were just bead on plate. This was 3/4 inch material we were welding. But submerged arc welding is a process where it was developed in the 1930s by Union Carbide, and Franklin Roosevelt wrote a letter to Churchill talking about this new welding process that was very efficient in the shipyards. So here's your plate down here, and you want to weld this little groove in a 1 inch or 2 inch thick plate, and you put this layer of flux, it's like sand, just pour it on the surface. It costs you $2 a pound today for this special chemistry sand. And the arc is submerged beneath the surface. You can sit there and watch, and all you see is a little puff of smoke and a little flash every now and then, and it's submerged beneath the sand. The arc is down here. You can run these things 600, 800 amps, and you can make great big welds very quickly, but only in flat position. You can't do it vertical or horizontal. But, I mean, Roosevelt wrote this letter in 1936 to Churchill about, well, it was 1936, but at some point. The patent came out in 36, okay, for this process, called submerged arc welding. And it's very efficient, but only for the flat position. That answer your question? Absolutely. Okay. But that was for steel. But the Soviets were publishing. There's there were two journals, Welding Production and Automatic Welding, and these were translated from the Russian into English by the Welding Institute in Great Britain, and they would come out a few years later. But you could go to the MIT libraries. We had these journals, and I would go and I'd read about these things, and there's a little more to that story. But the Soviets were publishing things up to about 1972. And then all of a sudden, this guy Gurevich, and here's Gurevich's text. When Jimmy Carter had detente, we had some Soviets come visit the lab, and actually some Soviets come and work in U.S. labs for 6 months, not at MIT, but other places. And Professor Pakadnia, who was at the Patan Institute, which is the world's largest welding institute. At the time it had about 5,000 people, now it has about 10,000 people. And we could talk about the Soviet politics of how you could end up with a welding lab that big. But it has to do with the guys in the Soviet Union. There were 7 guys in the Soviet Academy of Science that could hand out all the research money, like our National Science Foundation, Office of Med Research, all rolled into one. And they would send it to the different provinces. And Professor Patan was one of these 7 members of the Soviet group. And when it got to the Ukraine, which was the richest province in the Soviet Union, whatever you want to call it, he was head of the Ukrainian Academy of Sciences. So all the money came to Ukraine, he just got divvied up. And guess what? His lab was the best funded. Okay. Surprise, surprise. Anyway, this is getting a little ragged if you want. The Air Force translated it, okay, back in 1980s or something. But this is the book. I pass it around if you read Cyrillic. You can read it. I don't. But it has a nice letter in here that Pakadnia wrote to me, which they translated for me. Dear Professor Eager, we're glad to send you this book of our institute, blah, 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 okay, which you asked for us for during our visit to your laboratory. And that was Metabar on Pakadnia. Anyway, and here's a picture from the inside. Titanium, these are guys in spacesuits breathing air inside an argon chamber welding titanium. Okay, that's one way to do it. But you have to have a big enough industry and infrastructure to do that. There's a picture of the letter they sent me, in 1980 or whatever. Okay. Now, one of the problems is a creep fatigue interaction. And I remember after the Alpha Sub came out in 1980 at David Taylor in Annapolis, there was an Annapolis detachment then, right across from the Naval Academy. And that's where their weld lab was, and I used to spend some summers there and stuff. But we had a conference there on welding of heavy section titanium. It was a 2-day conference. First day was Industry Day. Boeing and McDonnell Douglas and Northrop Grumman came in. The heaviest section any of them talked about was a 1/4 inch. Most of them were talking 1/8 of an inch. That was heavy section to the aerospace guys. Okay. I was the only non-Navy person speaking on Navy Day, which is the second day, because I had this research project to weld the submerged arc welding. And the Navy had been spending, I don't know, $1 million a year or something, trying to perfect gas metal arc welding of titanium. But it was sort of a lower level effort, because one of the things the Naval Research Laboratory in Washington had found, one of the problems with titanium, there's something called a creep fatigue interaction. So fatigue, if you bend a paper clip back and forth, eventually it will break in fatigue, static clip loading. Oak Ridge and others had studied the effect of creep damage, where you just have a constant stress at temperature, versus fatigue damage. And ideally, you would expect, if there's no interaction, that on this plot you just have the black line. But they had found in some of their nuclear reactor vessel materials they wanted to make reactors out of, there was a creep fatigue interaction. And so basically a little bit of creep would destroy the fatigue life. Okay, that's the red line, 9 chrome, 1 moly steel. The Navy did some studies on titanium because, hey, when you're underwater, you've got a constant stress, compressive stress, and then if you go up and down, you'll have fatigue, cyclical fatigue stress. And I remember going to this workshop, and the guys in the Navy said, the Soviets came out with this stuff. How did they solve the creep fatigue interaction? I said, I don't know. And you know what the answer was? They didn't. Okay, that's right. I mean, you guys are starting to learn about how these Soviets work, okay?
Only a couple of times.
Well, they weren't quite as thorough about something. So my experience was, my first welding of titanium had to do with 1969. I was 19 years old. I was a summer intern in engineering at the Naval Air Rework Facility in Norfolk, Virginia. And it's the Vietnam War, and we had a TF-30 engine. Now this is an aircraft engine, and the typical life of one of these engines back in 1969 was 500 operating hours, okay, before you had to do a complete overhaul. And they needed more TF-30s in Vietnam, and we had to repair this. And they found a crack on the compressor case at the inlet. It was all boxed up, ready to be signed off. Someone finds it's cracked. It was going to be a 3-week tear down, re-tear down and repair. And so the manager of engineering decided we were going to repair it in place. We were going to weld it in place. We were going to stress relieve it in place. And he put me in charge of being the engineering person overseeing this. Well, what did I know? I was going to be a sophomore the next year, right? I'd finished my freshman year at MIT. I could spell titanium. But anyway, I go out and I watch this guy do this peening with a vibrating hammer on these little test strips. And then I had to go watch the guy weld it up, which wasn't, it's not too hard to weld titanium for a thin sheet. And then I had to watch the guy peen it to see if he stress relieved it properly. There was absolutely no reproducibility whatsoever on these test strips for the residual stress relieving, okay? But we had to get that engine out, right? So I come back in, and he said, well, you witness it? I said, yeah. I said, how'd it go? I said, I don't know, you know. He says, well, sign this. And he needed 2 signatures, okay? And I said, what does it mean if I sign this? He says, if that plane goes down, you'll be in jail within 24 hours. He said, oh, okay. So I signed it. Realizing that, okay. Anyway, so that was my first experience. I didn't do any welding, I just watched another guy weld. I got my first contract at MIT in August of '77 to do the Submerged Arc Welding of titanium. The Alpha submarine, I read about it on the International Herald Tribune coming back from Europe. 1980, we had a workshop on welding titanium. And during that workshop down in Annapolis, I was sitting there and I was kind of thinking back to all this literature I read about Gorevich's work. And I realized, you know, he quit publishing on Electro Slag about 1972. There were lots of articles in the 60s and early 70s, but he just quit publishing on it. I said, I bet you they used Electro Slag. And I went in and I told everybody, I said, I think he used Electro Slag. And they kind of shrugged their shoulder at me. I came back and the room 2 doors down, okay, we made the first Electro Slag weld outside of the Soviet Union or France. They made one in France. And it looked terrible. It looked absolutely terrible. But it deposited metal and it didn't use much flux. And the problem with the submerged arc process was it was using 8 pounds of flux for every 1 pound of titanium, and the flux was costing $100 a pound. Okay, and I determined this was uneconomical. Okay, I actually did a mathematical model to show how uneconomical it was compared to steel. And so I knew that submerged arc welding, while we might be able to make it work, was going to be an economic disaster. I made the Electro Slag weld, reported it to the Navy, and then what did they do? They, well, down here, in '81, they classified all titanium welding research. So I was out of titanium welding for a while, okay? Because you can't do classified research on campus. This weld that I passed around yesterday is a 2-inch Electro Slag weld. I might as well show you the next slide, which is a picture of electroslag welding, which is different than submerged arc welding, but you basically have two vertical plates. Anyway, two vertical plates, water-cooled copper shoes, a base starter tab. You feed electrodes in, and you're only going to use a few ounces of flux. And you just kind of, the flux is just a resistive heating element, and you melt the electrodes, and it makes it weld very quickly. We put down a 2-foot high weld in about 5 or 6 minutes. That's why it's such a bad weld. But in titanium, turns out to be a very efficient process. So that's a cross section through a 2-inch thick weld.
So this is one plate and this is another?
Yep.
And this is the weld between?
Yep, that's the weld, great big weld. I mean, the weld is half of that thing, right? And that's just a slice through it. That was made at Oregon Graduate Center where they could do classified research. Okay? It was given to people at that Oregon Graduate Center.
So the slag material was obviously also taken?
No, well, no, it's a calcium fluoride, strontium fluoride mixture.
So you don't lose strength there?
No, there's no slag on there. There's no slag in there. The slag just floats on top and you chip it off with a hammer afterwards. If you've seen them chip off welding flux on steel, the slag is just disposable at that point. And I'll tell you that half of this book is how to purify your fluxes. We were using reagent-grade single crystal calcium fluoride optical materials. There's a place out in western Massachusetts. This was the purest calcium fluoride we could find, and actually some of those things I sent around had some notes on them. And we could make welds that had lower oxygen and nitrogen than the base plate if we made them under this optical quality. But that's why I was paying $100 a pound. I was crushing up old pieces of optical crystals to make a flux that was just going to melt. But the Soviets they would take commercial purity calcium fluoride and strontium fluoride and other things, and they would melt them in a platinum furnace under a hydrogen fluoride atmosphere to get rid of the oxygen, okay, the calcium oxide. 1% calcium oxide impurity in your flux would destroy the mechanical properties of the weld in terms of oxygen and stuff. So very, very critical on the purity of the flux. Yes?
You said that there was slag in Nimitz, right? 'Cause I
The
said
slag is the yellow stuff, right?
And then it comes
there.
from a consumable guy as it goes in.
Yeah. Yeah.
The only reason why I asked that is because are those drums over there wire fed?
Those are wire fed.
So
Okay.
you're using wire fed that actually has a consumable guide around the wire?
Well, no, these are two pictures from two different things in the web, okay? I mean, one may come from the welding journal or something. You can have a flux-coated wire that you just feed in, or you can have a bare wire with flux that you just pour in like a submerged arc
I'm
flux.
only used to seeing stick with a consumable guide and then a wire where,
Yeah, and there are variations on all of these. But it turns out the world's, and the Soviets claimed that electroslag process was invented by Boris Paton's father at the Paton Institute. And he was a hero of the Soviet Union because during the fight with the Germans, he was repairing Russian tanks and getting them back out to the front, okay? And so he was a hero of the Soviet Union. His son became, took up leadership of the place when his father died, and his son became a very, very powerful political scientist, or scientist who was politically informed or whatever, okay, in the Soviet Union, and ended up controlling a lot of the funds. So there's a little interesting Soviet politics in it. Any other questions? This is something called deep TIG. It was called semi-submerged arc when it was translated from the Russian. Here are some welds. You can make beautiful titanium welds on this smaller one. If you look on the end, there's a weld on both sides. And if you weld in the presence of a flux, you can make the exact same welding parameters, but in one case you'll get a shallow weld, in the other case you'll get a deep penetrating weld. And it turns out, they call it deep TIG, or gas tungsten arc welding. The Soviets had been publishing on this since the mid-60s. No one had really been paying much attention to it. I came back and made some of these soon after the Electro Slag. And it turns out, without getting too much into things, in '81 I was invited one of the only 2 times I've ever used my security clearance, to see some foreign technology down at Annapolis. And now it's been more than 30 years, so probably declassified, but I don't know, okay? But I can tell you that the way they built the Alpha Sub was Electro Slag. Okay, I'll tell you that. You could figure that out because you can see the research and papers published by the Navy after 1980, okay? They were doing it on steel and other things, but they were really interested in the titanium. Okay, if I stop here, unless, you need to stop here? Do you have a class? Anybody have a class?
I don't know about.
Ours is 9:30.
9:30? You want to go a little bit later and finish up the other stuff on titanium? Is that all right?
Yeah.
Okay, so, what else? So, General Electric electron beam welding. So I got a call about mid-1980s from a guy at General Electric here in Lynn, Massachusetts, that are welding up a titanium compressor case. They took 2 pieces of titanium worth about $25,000 a piece. They're going to go into the jet engine and weld them into 1 piece that was worth about $70,000. Okay? And they had been doing this for years on this engine and had no problem. I had a research contract to do resistance spot welding in the mid-80s with these guys. And one of their engineers calls me up and he says, Tom, can you help us on, we have a problem on welding titanium. And I listened to him and I said, Lyle, you've got to, when you clean it with acetone, I told you have to use white gloves and stuff, and they were using white gloves. I said, when you use acetone, you've got to use reagent grade acetone, because most acetone has a little bit of grease in it, okay, unless it's reagent grade. And when you clean it with acetone, there will be a thin film of grease on there, and that grease is going to introduce hydrogen, which introduces porosity into your weld. You've got to use reagent grade acetone. Okay. So about 3 weeks later, he calls me up and says, Tom, we're still having this problem. It's costing us $250,000 a month. Can you come up here and help us with this? I said, okay. He says, oh, by the way, we don't have a budget for this. Can you do it for free? Okay, I had a research contract with him, so I said, okay. So I go up there, and I'm there. I show up at 7 o'clock in the morning in Lynn, and he walks me through the cleaning process and everything. It's a good cleaning process. And we go into the electron beam welding room, and 17 GE engineers show up. Now, I don't know what they were charging their time to, because I know that no GE engineer does anything without an account number, okay? But they must have had some account number for those 17 people to be there. And so I'm sort of the center of attention, and I was interested in seeing the surfaces before they put the 2 of them together to electron beam welding them. And I'm sitting there, I just inspected over here, and I'm looking over here on the surface, and I look back over there, and there's some white specks that were not there 10 seconds ago. It was raining white dust, okay, in this room. And I said, what's that? Well, and the foreman said, he had already cleaned that. If you would let him do his job, and he would have had it all put together without any of the dust. At that point, everybody decided I was a doofus and didn't know what I was doing. And so I went and I looked and I found over there, everybody's no longer paying attention to me. They're going to get the thing in the machine. And I found a little glass slide. And I took out my handkerchief and I cleaned it real well. And I took some of that acetone that he was squirting on there, because I'd asked if Lyle had gotten reagent grade acetone like I suggested, and he said no, he hadn't. Okay, well, thanks for listening. I have a picture of there's an electron beam weld machine. So there's the type of machine that has a little turntable, the electron beam welded. And I took the acetone, squirted it on there, and blew it off to dry it. And I could see Newton's rings. Anybody know what Newton's rings are? You ever seen oil slick on water? And then a little layer of oil on top of the flat surface. And you get interference colors where you have a quarter of the wavelength of light with the thickness of the oil. And I showed a couple of people Newton's rings and their acetone, and they all ignored me. So we went 11 o'clock, and Lyle says, well, let's go have lunch while the system's pumping down. We came back after lunch. It had a leak, and the vacuum system wasn't working. I said, oh, I'm going. I said, well, you get some reagent grade acetone. And so, next thing I hear, about 3 weeks later, they had welded up 6 of them, and they had not had any porosity since he got the reagent grade acetone, which is what I had told him to do 2 months before. And he was complaining because all he got for saving them $250,000 was a letter of commendation. And I thought, I didn't get anything. Anyway, so there were a couple of other, so welding titanium, this is an LCS, isn't it? It's a hydrofoil or something, but they made one titanium LCS, apparently. That is a titanium LCS as a prototype. I mean, it's the right color for titanium. It's not aluminum, unless they painted it as plain. Anyway, titanium welds can be very, very pretty, but they can also be contaminated with air very easily. So one time in the late 80s, I came back from a trip to Japan, and I had an emergency call from Engelhard, was making catalytic converters for Boeing. And I said, well, what are you making catalytic converters for an airplane for? Well, it turns out there's a lot of ozone up there. And if you breathe ozone for 3 or 4 hours or 5 hours across the country, you'll have a headache. And so the air you breathe has to go through a catalytic converter to get rid of the ozone. And they were rolling out the 747-400, so we date it by that, I guess. And they had 2 catalytic converters in there, what looked like this, that Engelhard was putting the platinum catalyst inside there, but Engelhard had to weld it. And they had 4 welds they had to make, 1, 2, 3, 4. And it turns out they were getting a 50% reject rate on their welds. And they only got 1 try to fix, okay? So if you think about this, the odds of ever making a good converter were near 0, okay? And I said to him, I said, look, I don't have time. Just got back from 2 weeks in Japan. What do you clean it with? Okay, acetone. I said, okay, make sure you're using reagent grade acetone. I told them on the phone how to do it. And they called back and they were delighted. You know, they had just made 10 welds and 9 of them were good, okay? Because they were cleaning it well. They were using white gloves. There weren't fingerprints on there, but again, it was whether you're using clean acetone. Thin films of grease that you can't even see. And they called me back up about 2 weeks later. They fell off the cliff. They were back to 25% good welds. Can you come by? Well, okay, I'm going to be down in New Jersey on something else. If you'll hang around until 6 o'clock, I'll drop by before I get a later flight back. And so I go by, and guess what? They weren't following the procedures I told them about that got them out of the hot water. They'd gone back to their old procedures. So I said, well, why don't you try following the procedures again? Okay. So cleaning, the point is, would most of you consider shipyards white glove facilities? No. Okay. So that's why you're not going to build titanium soaps in shipyards. So let's go to the Alvin. And actually, I do have a handout here for you on the Alvin. You can pass that. This will be on the, here, let me just have one so I know what you're handing up. By the way, Jerry has got Stellar up. You'll find the cognitive style of PowerPoint and the Gettysburg Address and 8 PowerPoint slides. This that I just handed out is from a National Research Council. This is the study I was on, Future Needs in Deep Submerged Science. And this was, could the National Science Foundation, originally when the Alvin was built in 1964, it was Woods Hole and the Office of Naval Research. The Office of Naval Research was formed after World War II by the U.S. Navy because the Navy could do things without an act of Congress, and they could start doing research. There were so many successful technological things like radar and stuff. By the way, you know radar, the home of radar is 3 doors down. There's a plaque on the wall there. That's where the first Klystron, it was like 1939, we weren't in the war, the British were fighting the war, and their physicists had invented this magnetic, or this microwave amplifier, but they didn't have time to develop it. And so there's a book written, I loaned it to someone once and they kept it on a no return plan, called The Most Valuable Cargo Ever to Cross the Atlantic. And it's this Klystron, okay? And it came to 8133 or whatever the room is down there, or 4133. And I remember in 1995, I had that laboratory, that's part of my lab, and I got a request from the BBC to come and videotape something in that room. I said, it has nothing to do with radar anymore. And they said, oh, we just want to go, for the history, the 50th anniversary of PE Day, we want to take a picture. Fine, okay. But that was the beginning of the whole radar thing. MIT employed, I think the plaque says 3,600 people were working on building radar sets during World War II and shipping them off, okay? Anyway, so there was this ONR in 1972 was told by the U.S. Congress, Mike Mansfield. The Mansfield Amendment said the U.S. military should not do any research, fundamental research, unless it has a military need. And the Office of Naval Research was actually the precursor for the National Science Foundation. The U.S. Navy in 1946 started ONR out of petty cash or whatever, and to do fundamental research. And when Congress decided we needed a National Science Foundation, they modeled the National Science Foundation after ONR, okay? The Navy was sort of the basic research leader there. But they, after the Mansfield Amendment in '72, they had to get rid of the Alvin, okay? And so they turned it over to the National Science Foundation and Woods Hole. Woods Hole is down here in southern Massachusetts. And that's the home of the Alvin. Here's the '64 Alvin. You can see a couple of white caps there in the audience. As the Navy paid for it. It was a steel hull originally. Somewhere around 1970 or so, they switched it out to a titanium hull. And that was partly because the Navy was trying to build their expertise up with titanium. And I'll tell you another story about the Seacliff, which was another Navy submersible. But anyway, the Alvin came around to this, that they call the new Alvin. And I was on the committee to figure out whether for $25 million, which is what NSF was going to have in their budget around 2007, whether they could afford to build a new Alvin. And that's what this study is all about. Before that, there was undersea vehicles national needs, which if you're interested in deep oceanography and stuff. Out of 36 people or so on the committee, I was the only person who knew anything about how to make something out of titanium. Everyone else was a biologist, marine biologist. They wanted to use it, okay, to do science studies. And they were going to justify why the National Science Foundation. But I had to figure out whether I was the only one who was going to be able to figure out whether they could afford to build one. And there's a little story to that. This is a eye test. It's not my slide, but it came off the web. But a little history of the Alvin. We'll post this as far as that goes. But in '66, it was the Alvin that found the H-bomb the Air Force dropped into the ocean off Spain. Okay. And so all of a sudden it became a hero ship, okay? Because that was a major problem. Who was going to get to the H-bomb first? Us or the Soviets, okay? And as a result, in the late '60s, the Navy and the Thresher disaster, the Navy spent a lot of money on deep sea rescue vehicles and things like that, okay? And the Seacliff and whatnot. So the Alvins do upgrades. Before it just sank to the bottom, and depending on how much ballast you had, that's where you went at that level, okay? The new Alvin actually has self-buoyancy, so it can stop on its way down, do things, and then go deeper and stuff. It has new syntactic foam. I'll talk about what that is. It has 5 ports, and so it's ergonomically better. And it has a we did determine we could build a titanium sphere. At least we thought we could do it. Lithium-ion battery, so it's just like your Samsung 7 Galaxy blows up everything. So syntactic foam. Until the offshore guys started doing deep ocean work, really syntactic foam was only for these deep sea submerged vehicles. But it's little glass spheres that are packed inside a resin that hopefully will not biodegrade in the ocean and break under extremely high pressures. And it turns out they're getting this down to less than 30 pounds, less than 50% of the density of water, okay? And some of it's getting down closer to 40% of the density of water, which is great because they pack every little location with the buoyancy foam. It can be machined to any shape you want, and every available space inside that alvin is packed with buoyancy foam, so it will float to the surface. So here's the sphere, better ergonomics inside with the viewing ports, and here's the sphere with 5 viewing ports. You can see 2 on the side, 3 in the middle. Here, and I believe this is probably a Carter rock, here's the sphere going under in its pressure test. It's about, I don't remember, a little over 7 feet in diameter. This chamber is just a little over 8 feet in diameter because I believe this chamber was built for the Sea Cliff to do the qualification of the Sea Cliff, which was a Navy vessel. We looked to see if, because the Navy had decommissioned the Sea Cliff, but they still had the titanium hull, which would have been good to use, except they couldn't, it was too heavy to put a Sea Cliff on top of the Atlantis. The Atlantis had only a 30,000 pound hoist capacity or something, and you had to have 40,000. They would have had to buy a new ship for $20 million, okay, or whatever. So we couldn't use the Sea Cliff. Here's a picture of the Sea Cliff. Looks similar to the Alvin, and I don't know what its missions were. I think a lot of its missions were classified. But in fact, it was built at Mare Island, and it was built as a demonstration of welding, in part, a demonstration of welding titanium. And the Navy tried for 6 months at Mare Island to use gas metal arc welding of titanium. And they couldn't do it. And they finally gave up and welded it with gas tungsten arc. Now, gas tungsten arc is the tortoise and the hare. I mean, gas metal arc is the hare running fast and laying down several pounds an hour of titanium. And gas tungsten arc, you're going to talk about ounces per hour. Okay, so it took forever. You probably had 200 passes in this 2 1/4 inch thick hull on the Sea Cliff. Just took forever, but they could do it with TIG, more distortion problems and other things. But the whole thing's machined to a perfect sphere afterwards, because you have to have a perfect spherical shape for these things under such compression, right? So they built the Sea Cliff, but they learned that you couldn't use, this is in the 70s, gas, well, they still didn't believe you couldn't use gas metal arc. I think they finally learned you couldn't use gas metal arc. In 1980, I got to go to the Baton Institute as the close down of Jimmy Carter's detente, okay, with the Soviet Union. And there were 3 scientific exchanges. The first one had 37 metallurgists. This is on the metallurgy program. The next one had 12, and the last one had 2 of us. This was the first one I went on, and the only other person who wanted to go was Julian Sekeli, who was a professor here, and he'd grown up in Hungary. He had actually been part of the revolution, in the Hungarian Revolution in '56, and I said to him once, I said, well, when you left Hungary, you weren't carrying a rifle, were you? He said, oh yeah. I said, well, how'd you get out of Hungary? He said, just took the train to the border and walked across, okay, with his rifle. And then he went to Imperial College and eventually became a professor here. But there's a whole, I could teach a whole lesson on the experiences in the Soviet Union. We were followed constantly by about 30 or 40 young consul. Okay, it was an interesting event. So the Alvin, the new Alvin has an emergency separation, and so this is the sphere and a lot of buoyancy foam, and if you have a problem, you just leave the heavy batteries behind and pop to the surface. But the problem with the Alvin is they still have not had that. Okay. So there's a little bit on titanium, commercial and military.
They still use steel balls to drop to go back to?
No, that was another thing. And they weren't steel balls, they were lead. Can you imagine putting lead in the ocean, a few pounds of lead in the ocean? The environmentalists were aghast that you'd have a couple 100 pounds of lead you'd leave at the bottom of 20,000 feet in the ocean. Can you imagine the pollution coming from that? All those dead fish who had brain damage, okay? Anyway, they now, actually, you're right, they do have steel balls now. They did switch to steel because iron oxide is considered non-toxic. If you go over to Harvard School of Public Health, iron oxide is the non-toxic control when they do tests. You can breathe iron oxide, you can get what's called siderosis, you get iron oxide, and they see dark x-rays because the iron is extra dense compared to your regular lungs. But then they find, that's one of the things they find about people who weld. If you've been welding for 30 years and they do a chest x-ray, you will have siderosis. You've been breathing welding fume all those years and you have iron oxide in your lungs. They also find that in the next 10 years, your body will slowly expel it and you will get rid of it. There are no known toxic effects, okay, from that. But, so iron, you're actually right. As I think back, they switched from lead to iron as their ballast. And so the way they do go back up is they start out with this bunch of steel balls and they can, they can drop some of them and the environmentalists are happy. So you're right, it is steel balls. But it was lead. And that was so. How to get the lead out. Okay. See you tomorrow. We'll start talking a little corrosion, I guess. Right?